Okay, so let us start with the questions of week 5 assignment. So question number 1 is, consider the state psi is equal to 3i phi 1 minus 7i phi 2, and another state chi as some linear combination with coefficients with phi 1 and phi 2 again, where these phi 1 and phi 2 are what? They are basically they are the orthonormal unit vectors or basis vectors, you can say. So because they are orthonormal, I have already told you the meaning of orthogonal. That means they are orthonormal. That means they are orthogonal within themselves, within each other, but they are normalized within themselves. And it is asked, they are asking you that the states satisfy the triangle inequality or not. So first of all, you have to know what is the triangle inequality actually in quantum physics or quantum mechanics. So the triangular inequality statement we have to start with, and then we have to prove using the state psi and chi whether they satisfy this inequality or not. So let us choose a page and start solving it. So by triangle inequality, you mean that if there is two states psi and chi, then psi plus chi, if this is a combined state of both of them, then if you take just this normalization of this state and take a square root of it, right? So this will be less than or equal to the individual states normalization square root. Psi normalized square root plus chi square root. So this is the, then if this is true, then this is satisfied. Okay, so either equal to or less than. So individual thing will be actually greater than the net things actually square root. So this is the idea. Now we have they have provided us with information of what is psi and what is chi. So let us write down first what is psi plus chi. So that is let us go back and see. So it is 3i phi 1 minus 7i phi 2 and minus phi 1 plus 2i phi 2. So this is 3i phi 1 minus 7i phi 2. Then what is the other thing? Minus phi 1 plus 2i phi 2. So then it will be 3i minus 1 phi 1 minus 5i phi 2. So this is the whole state, right? Now what is this thing? This thing is basically this psi normalization. So that means you have to take minus 3i phi 1 plus 7i phi 2, that with plus 3i phi 1 minus 7i phi 2. Now remember that phi 1 phi 2 are all orthonormal. That means phi 1 this is 1, and phi 2 with phi 2 this is also 1, but phi 1 phi 2 equal to 0, and also phi 2 phi 1 equal to 0, since they are orthonormal. So using this condition, okay, now so naturally you only have to take items having either both phi 1 or both phi 2, and the cross terms like phi 1 to phi 2 will be 0, and phi 2 to phi 1 will also be 0. So that are not, those are not required. So first of all, with phi 1 you get to see minus 9 I1 square, and this is 1, phi 1, phi 1, and then 7i minus 7i, which is like minus 49 I squared into 1. I square is minus 1, so this is plus 9 plus 49, so this is 58. Similarly, chi this normalization will be minus phi 1 minus 2i phi 2 minus phi 1 plus 2i phi 2. So this is minus minus plus is plus 1. Again this will be 0 and this will be 0. So this thing is minus 4i squared into 1. So this is 1 plus 4, which is 5. Now then, what is psi plus chi and psi plus chi? This normalization is basically 3i minus 1 and another minus 5i. So 3i minus 1 is minus 3i plus 1 phi 1 plus 5i phi 2 up to 3i minus 1 phi 1 minus 5i phi 2. So this is again ignoring the cross terms leading to 0, only taking phi 1 and phi 2 terms. So this is minus 9i squared minus 3i plus 3i minus 1 into 1 minus 25i squared. So this is plus 9 plus 25 equal to 34. So let me check. I think there is a may have been a mistake. So okay, so there was another minus 1 which I did not take here. So this is minus 9i square minus 1. So this is minus 1. That means, or so this was minus, I think, what was that? Okay, minus 1 minus 3i and minus 1 plus 3i. So I think there is this. Oh, sorry. So there was 3i minus 1. So here it will be minus 3i minus 1, and this will be plus 3i minus 1. So this is minus 9i squared minus plus 3i, then minus 3i, minus minus plus 1. So this is plus 1. So this is 35 actually. Now if you say that this is 35, this is individually 5 and 58. Now if you look at this relation, what you get is that on this side you are getting 35 and on the other side you are getting 58 plus, I think, 5, right? So which is like 63. So obviously 35 is less than 63. That means this condition of triangle inequality is satisfied. So under this condition, that it is not equal to, but it is less than this. So either of these, if is satisfied, either equal to or less than, then we can say the triangular inequality is satisfied or followed here. So this triangular inequality is actually true, that for this state it is valid. So our answer will be that the answer is true. Yes, this triangular inequality is satisfied by these two states, psi and chi. Now, question number 2 is that consider two operators A and B which are Hermitian and commute. Then the operator A plus IB by root over A square plus B square is unitary or not, you have to prove. So, let us see here that A and B, they are both Hermitian and they commute. Hermitian has first of all means that A dagger is equal to A and B dagger equal to B, because they are Hermitian, and since it is said that they commute, that means AB commutator bracket is 0 or AB equal to BA. So these are the two conditions on these two operators that is already given in the question. Now it is asked in the question that operator a plus ib. So let us write down this new operator. Let's say this is O operator, which is formulated by some combination of a and b, a plus ib by root over of a squared plus b squared. Now, how to prove that this is unitary? So, first of all, to say that this is unitary, you have to satisfy this condition that O dagger equal to I to be unitary. So, this you have to check whether this condition is satisfied or not. Now, you already know O. So, what will be O dagger? So, O dagger will be plus IB dagger. Now, this thing A squared plus B squared, so the dagger operator does not do anything on this, so this remains the same, right? So only dagger operator operates on the upper term, so which is making it, let's say first of all take the whole dagger only, because this is the whole operator's dagger, which will be like A dagger minus I B dagger, because I becomes minus I under dagger and A and B individually takes the dagger sign. Similarly, the bottom it has A dagger squared, now B dagger squared. Now in the question it is already given in the condition that A, B are both Hermitian operators, that means A dagger is equal to A and B dagger equal to B. So it is A minus IB by root over A squared plus B squared, right? So if this is this, then let us check whether this condition is satisfied or not. So O dagger will be A plus IB, then A minus IB, then root over of A squared plus B squared whole squared. So this is A squared minus I AB plus IBA. So this is minus, if we take common, then this is AB minus BA, then minus I squared B squared divided by root over of A squared plus B squared. So this is already this commutator relation. From this we know that AB minus BA is 0 because they commute, right? And so this becomes A squared and I squared is minus 1. This is plus 1. Okay. So this thing we are getting, sorry, this was whole squared, right? So this is no square root anymore. The square root sign will not be there. So then you get that you already have this and this cancels out. This is I, which is the unitary sign. So that means you are getting LHS equal to RHS. So this is proved to be true, which means this operator, new operator O, is unitary. So our answer will be that the operator, this new operator is unitary, that is true. Now question number 3 is consider a one-dimensional particle with the wave function. So up to this is basically this question number 2 solution. Okay. Then question number 3 is psi xt equal to a one dimensional particle wave function is sine pi x by a to the power of minus I omega t. Probably you can recognize from the form that it is of the form of a particle in a box type of wave function, because there you used to have wave functions like sine n pi x by a, and n value could be taken from 1, 2, 3 etc. integer values. So the ground state is for n equal to 1, and here actually the ground state is given because you can see that sine pi x by a is given, or n equal to 1, and this is the x dependent part, and this other part e to the power of minus I omega t is nothing but the time dependent part of the wave function. That you also know, because the wave function has one x dependent part and one is the time dependent part. Now the x dependent part is taken care of by this eigenfunction sort of a thing, that is for this case of the infinite potential wall or the particle in a box type of problem. But the other time dependent part comes from the term like e to the power of minus I et by h cut, right? So that is the factor that adds up, that multiplies to the wave function for making it time dependent. So this is e to the power minus I et by h cut, where E is in this case the eigen energy of that particular state. So because it is a particle in a box kind of problem and n equal to 1, so you have to choose what is the ground state energy E1 for this case, and if you put that, it will be like a form of e to the power of minus I omega t, right? So this is just for your understanding, that to identify or recognize what wave function is actually used might be helpful in some cases. Now the particle is confined between 0 to a. The probability of finding the particle in the interval is what? Now, one thing is that uh, because it is a particle in a box and the box size is a, obviously the particle will be confined between 0 to a. But the probability is has to be specified by you in a particular interval of x, which is from a by 4 to 3a by 4. Now, what is the technique to do that is that basically you have to take Psi Kate, Psi, Bra, this whole normal inner product, and then take uh, the inner product and solve it in an integral type of a form, right? So after doing that, you have to take the integral limit from 8 by 4 to 3 by 4, whatever range that is given to you. And remember that if the wave function that is already given to you in terms of Psi is already not normalized, then you have to also divide it by the normalization factor, because ultimately for a physical wave function it has to be normalized. So by taking care of all those conditions, if you start solving it, so let us start that. This is question number 3, and this is a particle in a box sort of a problem, which is from x equal to 0 to x equal to a, the particle is confined, and rest of the part it cannot go because it is an infinite potential well. Okay, so the particle, let's say it is here, and now it can be anywhere inside this potential well or the box, but in the question it is asked that you have to specify the probability of it being in a certain interval, which is from a by 4 to 3a by 4. So what is the probability of doing that? Now the particle wave function for first excited for the ground state in this case is given as Psi. Okay, and then uh, you have to find out the probability, right? So the probability will be probability of the particle a by 4 to 3 by 4 interval is Psi whole mod. Okay, and Psi whole mod, then this is the probability. Now we have to take it in an integral form. This Psi star Psi dx for x equal to from a by 4 to 3a by 4. Now to normalize Psi, so this is not the normalization because this is not within the full range. So to normalize you have to take the full range of the wave function, which is from 0 to a. Now to normalize you have to divide by normalization factor. Okay, and that is 0 to a. This is the normalization factor squared because so this thing has to be 1 to normalize. That means this is normalization factor. So let's say, so basically if your normalized thing is like Psi prime, or which is normalized as by normalizing factor a Psi. Now then for normalization condition is Psi prime is equal to 1, or this a squared Psi star Psi dx from 0 to a, this whole range equal to 1. So then basically a squared becomes 1 by 0 to a Psi star Psi dx, the full range. So the normalizing factor A becomes 1 by root over of psi is normalization inner product up to full range like 0 to A and the square root. Okay, so if this is the normalization factor, then to get the probability of being like this, then you have to take the, because each one of psi will be having this A as a factor, and so both of them comes together as A squared, that means the square root will be gone. So the probability with normalize, so this is very important, that if you do not normalize your wave function, then the probability information that you are getting is not actually the right answer. So to ensure that whether the wave function already provided to you is normalized, if yes, then okay, you don't have to do anything else other than this form, but if no, then you have to also take care of the normalization factor within this probability value. So the probability with normalization function, normalized wave function is psi from the probability on which range you have been asked to calculate, divided by the actual normalization is from 0 to A, which is like um, so the top one will be A by 4 to 3A by 4, and psi star psi dx is sine under star operation remains the same, so this is sine squared pi x by A, and there was e to the power of minus I omega t, which becomes e to the power I omega t plus e to the power minus I omega t. So because there was psi star psi, so this whole thing becomes actually e to the power of 0, that means 1, right, and do not contribute. So this is up to dx, and bottom is the same thing, but only the range will be different from 0 to A full range, sine squared pi x by A, same to the power 0, which is 1, and dx. Okay, so then you have on the top sine squared pi x by A. Now you know how sine squared integration is being done. So sine squared pi x by A dx equal to half 2 sine squared pi x by A dx. Now this is a formula for 1 minus cos 2 pi x by A dx, which is half into x. Cos to integrate will be sine, so sine 2 pi x by A into 1 by 2 pi by A is A by 2 pi plus some integration constant. So this is half x minus A by 2 pi sine 2 pi x by A plus c. Now when the integral limit is between A by 4 to 3A by 4, then it is half, there will be no integration constant, just the value of x will be put into. So this is 3A by 4 minus A by 2 pi sine 2 pi by A into x is replaced by 3A by 4. So this is 3 pi by 2 sine 3 pi by 2 minus of A by 4, and minus minus plus is A by 2 pi sine 2 pi by A into A by 4, which is pi by 2, divided by 0 to A, this whole thing becomes A minus A by 2 pi sine 2 pi A by A, which is sine 2 pi, minus everything is 0. So what you get is that half and half cancels out first of all, and then top one is 3A by 4 minus A by 4 is 2A by 4 minus A by 2 pi sine 3 pi by 2 is actually minus 1, that you know already, that sine 3 pi by 2 is minus 1, then minus uh, A by 2 pi sine pi by 2 is plus 1. So this is minus minus plus, and this is minus, so this and this cancels out to be 0, and the lower one is A minus sine 2 pi is anything is 0, so this is 0. So you are getting 2A by 4A, which is uh, okay, hold on a second. So 3A by 4, and then mm, half. So I think I have made a sign mistake. So this is 3a by 4 minus of a by 2 pi into sine 3 pi by 2 is minus 1, of course. Then minus a by 4 is making it 2a by 4, but this is, so this is minus 1, so this is making it minus and minus plus 1, and this was not minus, this was a plus sign. So there was the mistake I have been doing, that this is plus sign. So this is a by 2 pi into sine pi by 2 is plus 1. So this will be so this will be 2a by 4 plus a by 2 pi into 2 by whether the lower part was okay or not. So this is half plus this is a minus a by 2 pi, then 2 pi part is sine 2 pi is 0, so this is 0, and then other things will also be 0, so this is simply a. So then it makes it 2 plus pi plus 1 by pi a. So this is 2 pi 2 plus pi. So if you calculate, you will get somewhat answer like 0.82. So this is your answer, that this is 2 pi 2 plus pi by 2 pi, which is nearly 0.82, which is the probability of finding the particle within this space that is given to you. So the answer will be 0.82 or 0.8 somewhat, which is actually, if you check their given answer, this is between this order, so this is matching. Now question number 4 is, a system is initially in the state psi naught, which is given in the combination of phi 1 to phi 4, and phi n's are the eigenstate of the system's Hamiltonian such that H acting on phi n giving n square psi naught epsilon naught phi n. If the energy E2 is measured, its value and the probability will be respectively what? So let us solve it here only, because there is enough space for solving it. So our state is initially given by psi naught, which is a combination of all these four basis states, like, so linear combination of all four of them, which are very interestingly the eigenstates, the direct eigenstates of a, sorry, so this by root over 7. So eigenstates of the Hamiltonian, that means that Hamiltonian H cap acting on a phi n is giving n squared epsilon naught phi n. So for E2, what would be for E2? So let's say H cap acting on phi 2 is 2 squared epsilon naught phi 2. Okay, so this is 4 epsilon naught phi 2, but because this is the eigenvalue equation, so this should be equal to E2 phi 2, where E2 is the eigenvalue corresponding to the eigenstate phi 2. That means E2 is equal to 4 epsilon naught, right? Now it is said in the question that energy E2 is measured, then its value and the probability will be what? So first of all, the value of E2 you have already obtained, that is 4 E naught. Now the probability of the E2 being measured you have to say. So you have to, for this kind of question, it's always important to look at what E2 belongs to. So first of all, E2 is the eigenvalue corresponding to the eigenfunction called phi 2. So how does phi 2 affect, how is phi 2 placed in the form of psi naught, that you have to find out first. So phi 2 is only one term which has this coefficient as root over 3 by root over 7, right? So that means you have to, if you take the probability of the system being in the state phi 2 basis, where the initial state of the system is psi naught, then you simply have to take the inner product of phi 2 psi naught whole mod square is the probability of system initially at psi naught state being in phi 2 state. Okay, so if that is the case, now again you have to remember or take care of one thing always, that is often we miss out, is that we have to ensure that whether the wave function you are dealing with is a normalized wave function. If not, then you have to add the normalization condition to it. Okay, you have to normalize it and you have to do all those things. So first of all, check that whether this is normalized. So how to see that psi naught inner product is root over 2. So first of all, this is root over 7 whole squared will be outside. So then only because they are orthonormal eigenstates, only the individual term within themselves will be contributing. So this is root over 2 squared, root over 3 squared, plus 1 squared, plus 1 squared, which is like 1 by 7, 2 plus 3 plus 1 plus 1. 7 by 7, which is 1. So it is fine that the initial state you have to start with is already a normalized wave function. That means it is a physical state. So that part is sure clear. Then to get the probability of this state system of state psi naught to be in the basis state phi 2, you have to take this value, and this bottom value, because it is already, we have checked that this is psi naught which is 1. So this does not contribute. So only the factor that is you are asked to calculate is phi 2 psi naught whole mod square of this inner product. Now how we are choosing this form to get the probability of the system being in this state comes from a pretty simple thing. I think you have already learned about it in the lecture. So this is basically, if you have a general state fx, which is a linear combination of all states as phi and x, which are like eigenstates here, and each of these states, how they are contributing to fx is via this coefficient term, which is cn. Okay, so this is a summation over all different values of n going from 1, 2, 3, etc. Now probability of this state being, so it can be in any of the eigenbasis states, but the probability of being in a particular phi n basis is basically phi n fx, okay, which is like phi n cn phi n. Now you know that whatever combinations are there in the summation of expression of psi naught, all of them will have a inner product 0 with phi n basis, because they are orthogonal to each other, and only the phi n to itself will be normalized. That means only contribution will be from uh, phi n itself, so which is cn times cn into 1 basically. Now for getting the probability, you have to take a whole mod square of this. So the probability is the coefficients whole mod square, which is like phi n fx whole mod squared. Now if that is the case, then phi 2 psi naught whole mod square is basically uh, phi 2, how it is present in psi naught is root over 3 by root over 7. So that is root over 3 by root over 7 whole square, which is 3 by 7. So the probability of it being in the state phi 2 or being measured as E2 is basically 3 by 7. So your answer is 4 E naught and 3 by 7. Okay. Now question number 5. So this is question number 4. Let us draw a line so that don't get confused and mix it up with other questions. So this is question number 4 up to solution. Okay. Question number 5 is, you have given Lz, which is the angular momentum operator, Lza, that is a commutator bracket of Lza, and within the basis state is Lm. So this is the standard basis for angular momentum thing, because these are the orbital quantum number state Lm. So do not focus on that for now, just consider that that is a state that is given to you, and that is like a basis state or eigenstate, whatever. So now this is given that this relation is satisfying. Commutator bracket under this, like expectation value, if you think of it, is giving you I h cut for an observable random general observable A. Then the expectation value of zpy is how much? So to solve this, first let us choose this page. This is L M, this is L Z and A, commutator bracket L M is equal to I h cut. Now because A can be any general operator, so why not take A equal to the new operator that they are giving us is zpx, right? So then Lm Lz zpx Lm will be satisfying the formula of I h cut. Now what is Lz zpx is basically Lz is L is r cross p, right? So L is r cross p, it is the angular momentum, where p is the linear momentum and r is the position. So if you follow this cross product from there, you know that Lz, the z component of L, will be simply x py minus y px. All are operators, right? So once you know this, you put the value of L here. So this is x py minus y px comma z px. This is the commutator bracket relation. First of all, let us simplify it this form, that x py z px minus y px z px. Now you know that the canonical variables has this relation that x px equal to I h cut and px x will be minus I h cut. Similarly, y py equal to plus h cut and minus y py y equal to minus h cut. Similarly, for each of them, for z also this will be satisfied, but with themselves x equal to 0, with themselves px equal to 0, and it can be not only x but also y. And the other thing is that x with py will give you 0 and not I h cut. Okay, so this is only for similar variables that it canonical relation satisfies, but x pz is also 0. Okay, so by knowing this formula, you have to carefully do the commutator bracket. So this is x so this is basically you have to take that whether or we can directly instead of and one thing is that you can figure out and you can derive this whole thing in terms of x and px, and the other quicker thing to do is that if you already know the relation of L with the other variables, then commutator bracket relation you can directly use and solve it much quicker. But if you don't remember that, you can always like disintegrate these parts and break it down in terms of x and px and then solve it like I am doing here. But to save our time, what we'll do is that we'll directly use the relation for Lz with the other operators, which is, so this kind of an operation means that this is z cap Lz px plus Lz z cap px. Now Lz has x py and y px, right? So this is equal to z x py minus y px. So these are all operators, so hat sign has to be there. Sometimes I may miss it, but you remember that these are under hat sign. So this Lz z is basically x py minus y px comma z px. You see all of them are x and y, but this is z, so obviously this will not cover, this will not be give you any finite value, so this is already 0. The first part has some hope because there is x px and px, okay, and there is px and py, so that may work. And not those, but there is mainly x and px, which gives you plus I h cut from the commutator bracket. So this is non-zero value to some extent. So how to solve this? This is z cap, then this is x comma px py plus x py px. So this part is already 0 because they are non-identical variables x and y. Then minus y px, this will also be 0 because they are of the same term. And then minus y px, this is also 0 because they are y and x different canonical variables. Now only term that contributes is this term, so this is I h cut z py, I h cut z py. So this is basically what you're getting is that, okay, I h cut z py. Now so this term, if you start with what you started with, is now we have solved this inner commutator bracket relation. So by putting it in the known equation given from the question is Lz cap comma uh, Lz cap comma Zpx cap Lm. So Zpx cap Lm. This was given as IH cut as per the question. Now this thing has IH cut already, so this is IH cut Lm. So this is L M Z Py equal to 1. So this value you have obtained as 1. So let us go back and check that this expectation value is basically, expectation value of an operator is being sandwiched between the states that it has come from. So this is Lm this is we are satisfying from here, so the expectation value is plus 1, that means B. Okay, right. Now number 6 is a question on parity operator. So consider one-dimensional motion of a free particle and three operators, the Hamiltonian, momentum operator and parity operator. Then which of the following are commuting? So let us choose this page. Question number 6, that there are three operators, momentum operator, parity operator and Hamiltonian operator. So which of them will be commuting or satisfying the commutator relation, that you have to derive and solve. So this is, first of all, in the question it is written down that this is a free particle. Free particle is means no potential energy acting on there, that means Vx part is 0. So the Hamiltonian has a form that this is used to be kinetic energy plus potential energy, but because it's a free particle, potential energy term is 0, only the kinetic energy, which is kinetic energy, which is just okay. So we are discussing this question, that parity operator for this free particle problem, where how is the commutator relation of the parity operator and the other operators like Hamiltonian and the momentum operator. So first of all, the thing is that we know that this is a free particle, so it has no potential energy. So what is the form of the Hamiltonian operator? Is only the kinetic energy term, which is like p squared by twice m. Right, now this p square, p is a linear momentum, this is the capital curly P is a parity, this is the linear momentum operator, and this is the Hamiltonian. Okay. So then what are the relations that is given to you to prove in the options is, first of all, Hamiltonian with what was that? So Hamiltonian with momentum, let me check again. Hamiltonian with momentum square, then Hamiltonian with parity, parity with momentum square, and parity with momentum. So Hamiltonian with momentum squared is basically giving you p squared by twice m p squared, which is taking the commutator bracket within the same operator. That means if you ignore this p 1 by 2m, this is basically p squared into 1 by 2m, which is obviously 0, because they commute within themselves because they are essentially the same operator. This is only possible because this is a free particle in the question. There is no potential energy term giving you a x-dependent form, only the momentum is there. Now Hamiltonian with the parity operator, what does it give you is that Hamiltonian is here p squared by twice m only, and this is the parity operator p. Okay, so let us say this is the parity operator p, the curly one, and this is the form. So this is basically the relation between momentum operator square and the parity operator. Now whether this commutes or not, for that you can get what is momentum operator square and parity operator. So this is basically p squared p minus p squared, and let's say you are working it on some state psi, which is psi x basically. Now p squared is basically minus I h cut d dx, right? So p cap operator. So then p cap square is this thing whole squared. So this is minus I squared becomes, so this is this minus becomes plus, and I squares make it minus. So minus h cut square d2 dx2. So whenever you are operating p squared on psi x, what are you getting? It is basically minus h cut square d2 dx2 parity operator minus parity operator. Here this p square is acting on psi, which is giving you minus h cut square minus h cut square, and then double derivative on psi, which is psi double prime x, meaning double derivative on psi. Now here you are getting, so this is this, and here this is directly acting on psi x, right? So you are decomposing the both terms. So minus h cut square common take it out, and parity acting on psi x makes it psi minus x, and then you have a derivative second order term. Then there is a minus also here. This is a minus sign. Then parity acting on psi double prime, which is psi double prime of minus x, which is nothing but minus h cut square. So once you take derivative on psi minus x, so hp proportional to this. So yeah, so once you take double derivative on this, you will get another psi double prime of minus x, and also this is also psi double prime of minus x. So this is basically 0. That means p squared p, this commutator bracket is 0, and that also means that hp is also 0. That means they all commute with each other. Now, so with this we are proving three statements given in the option, that H commutes with momentum squared, H commute with parity operator, and this itself tells you that in the question itself, because this is proportional to this, so momentum square is also commuting with the parity operator. And the last option was that not squared but only the momentum operator and parity operator. So if it operates on psi x, let's say, so that means minus I h cut d dx parity operator psi x minus parity operator minus I h cut d dx on psi x. So minus I h cut you take common, and then it's d dx of psi minus x minus of parity operator of psi prime x. So it gives you psi prime. Okay, let me check. Uh, so this thing is actually that minus I h cut when you have d psi of minus x, so you have to basically take d of minus x, then psi of minus x, and there is a minus 1 that is compensated for here. So basically you are changing your variable from minus x as y, right? So to compensate for that you have to take another minus 1 sign, but in this case you are directly taking the x to minus x as this. So you are getting minus I h cut common, then here minus psi prime y minus psi prime minus x. Okay, and you are seeing that y is equal to minus x, so this is basically minus I h cut minus psi prime minus x, another minus psi prime minus x. So this is minus minus, this is minus minus plus, so this is 2 I h cut psi prime of minus x, which is not equal to 0. That means this operator commutator bracket, it does not commute, rest all three commutes. Now you may wonder why on the first derivative term it is not absorbing the minus sign within, so they are not commuting. But for double derivative, when it was for double derivative or p square was there, then d2 dx2 term was there. So for d2 dx2 this minus sign was taken care of, and that is why you are getting a commutator bracket of 0. So our answer will be that all the three are commuting with themselves but with the operator, but this last one is non-zero, does not commute. So the which one of them are commuting? So this one, and this one, and this one is not commuting. So this is the correct answer also. Now question 7 is the initial wave function of a particle in a harmonic oscillator potential can be written as this psi x0 is some linear combination of psi 0 and psi 1, where a is the normalization constant, psi 0 and psi 1 are the ground state and the first excited state of the harmonic oscillator, and they are orthogonal to each other. And then psi xt whole mod square can be written as how? So basically uh, psi xt whole mod square means you have to take, first of all you have to know what is psi xt, because you have been given in the question psi x0. You have to take what is psi xt. So let us choose a page. Psi x0 is given, okay, is equal to a 3 times I think psi 0 was there, and then plus 4 times psi 1, okay. And remember this is a harmonic oscillator problem. So for a harmonic oscillator problem, the eigenvalue and eigenfunctions are well known. So eigenvalue for a harmonic oscillator problem is n plus half h cut omega. So for ground state, it starts with n equal to 0, 1, 2, etc. integer. So for ground state, it is E0 for ground state, which is given as psi naught, which is has this energy half h cut omega. And the first excited state E1 is for n equal to 1 for first excited state, which is psi 1, which is like 1 plus half or 3 by 2 h cut omega. So this is a 3 psi naught. Now how do you get psi xt from here? You already know that to introduce a time dependent factor you have to multiply it by e to the power of minus iet by h cut. So this is the time dependent factor of any wave function psi xt, but because there are two separate eigenfunctions of this harmonic oscillator components divided in psi naught and psi 1, so instead of a single term it will have two terms. One is e naught and another is e1. So the e naught term will be with this and e1 term will be with this. So e to the power minus I e naught t by h cut plus 4 psi 1 e to the power of minus I e1 t by h cut. So this is a. So this is our form. Now it is mentioned that you have to take what is psi xt whole mod square you have to calculate. And so for that, first of all you have to know what is the value of a, right, because a was unknown there. So then you have to normalize this. So psi x comma 0 whole mod square equal to 1, or a squared, then 3 squared plus 4 squared, because the rest of the terms are 0 as they are orthogonal as mentioned in the question. So these terms are 0. So this is a squared 3 squared plus 4 squared equal to 1. So this is 25 equal to 1, or a equal to 1 by 5. Now for this term there is also this time dependent factor. Now if you choose, so this is basically a square taking out, then 3 squared psi naught is 1, or you can also say psi naught squared in this case. Then e to the power of minus and plus you have to combine. So e to the power of minus I e naught t by h cut plus I e naught t by h cut, because this whole mod square is taken. So this is e to the power 0, totally will give you 1. And the second term is 4 squared psi 1, again e to the power plus minus makes it 0, plus now there will be cross terms because there are not only psi naught psi 1 but these time dependent factors are also multiplied. So this is psi naught squared, this is psi 1 squared. Okay, and then you have 3 into 4. So first of all this term star into this term plus this, then the second term will be this term into this term star. So this 3 psi naught, this becomes psi naught star, then and here e to the power minus I becomes plus I because complex conjugation is taken, e to the power plus I naught t by h cut, into second term is as it is 4 psi 1 to the power of minus I e1 t by h cut. Then another cross term will be 3 psi naught e to the power of minus I e naught t by h cut into 4, the second term has complex conjugate psi 1 star e to the power of plus I e1 t by h cut. So this is 3 square means this is 9. Let us put the value of a square. We know a square is 1 by 25. Then 9 psi naught square plus 16 psi 1 squared plus 12 psi naught. Now you know that harmonic oscillator eigenfunctions are all real, that you know from your knowledge. So psi naught star will be equal to psi naught and psi 1 star will be equal to psi 1 because they are all real eigenfunctions. So these two, both of the terms are psi naught psi 1 in common, and then you have e to the power of I e naught minus e1 t by h cut plus e to the power of minus I e naught minus e1 t by h cut, which is nothing but this is your because you know e to the power ix plus e to the power minus ix by 2 is equal to cos x. So that makes it that this is 2 cos x or এখানে or here the x is I, sorry, not I, e naught minus e1 t by h cut. Okay, so overall you are getting this is equal to 1 by 25, 9 psi naught square plus 16 psi 1 squared plus, then this is 24 and 12, 12 into 2, 24 psi naught psi 1. Then this whole thing can be compressed as cos omega t, where omega is equal to e naught minus e1 by h cut. So here you get that by comparing the question, you have these coefficients already known. So from here you can follow the question that it was the b value was the first value with psi naught square. So b value was clearly, so first of all small a is 25, which was below. Then b value was the first term with psi naught square, which is 1, and the c value is with psi 1 square, which is 16, I think. Yeah, and the last value was d. B was 24, as you remember. So 25, 9, 16 and 24. 25, 9, 16 and 24. These are the also correct answer. So this is solved. Now question number 8. The Hamiltonian operator for a two-state system is given by some A, then 2 with this projection operator 1, 1, and then 3, 1, 2, two different operators. So bracket form notation is given. Now A is any dimensionless form, A has dimensions of energy, and the corresponding eigenvalues and eigenvectors will be what? So first of all, this kind of a problem, Hamiltonian has this form. This is easier to simplify it within a matrix form. So whenever your Hamiltonian is like this, that 2, 1, 1 minus 3, 1, 2 minus 2, 1. So this is basically the same form or as this, like this is the this term, and then 2, so 1 and 2 makes it this term, 2 and 1 makes it this term, and 2 and 2 is nothing given, so this is 0. So this is the matrix form that is given to you. So this is easy to get because essentially the matrix elements are given like this, that if the basis states are just 1 and 2, so like the form of this eigenvector is like 1 and 2. Okay, so for this the matrix elements will be h between 1 and 1, h between 1 and 2, then h between 2 and 1, and h between 2 and 2. So this is your final matrix form. Okay, and then once it is in matrix form, it is very easy to calculate the eigenvalue and eigenvector for a matrix. So this is A 2 minus 3 minus 1 0. So let us choose a page below. Now for this Hamiltonian matrix, this is question number 8. H equal to A 2 minus 3 minus 1 0. Now to get the eigenvalue and eigenvector, you know the determinant 2 minus lambda minus 3 minus 1 minus lambda equal to 0. This is A 2 minus 2 lambda plus lambda square minus minus plus again a minus 3 equal to 0. So this is lambda squared minus 2 lambda okay, so this is lambda is equal to this is 2 plus minus 4 this is 2 plus minus this is 2 plus minus, so either 6 by 2 or minus 2 by 2, 3 or minus 1. So these are the eigenvalues for this Hamiltonian operator. And what are the eigenvectors? So to get the eigenvectors, you know the form is h psi x equal to lambda psi x, where lambda has two values 3 and minus 1. So for first term 2 minus 3 minus 1 0, let's say psi x is given as the terms x1 x2. So this is, let's say, the psi x eigenvector is equal to, first value is, let's say, 3 as eigenvalue. So for here you get 2x1 minus 3x2 equal to 3x1, and another thing you get minus x1 plus 0 is equal to 3x2. So you get x1 equal to minus 3x2 from both. So your eigenvector for this lambda is equal to 3 will be x1 x2 is minus 3x2 x2. So you can take x2 as 1, so this is minus 3 and 1. Take x2 as 1. Now this is in a state, this kind of a bracket form. Now if you have to get, you can take it in a bracket notation. So that is basically, this corresponds to the state 1 and this corresponds to the state 2. This is minus 3 1 plus 1 2. Now you have to also have to normalize, because otherwise you cannot represent a real state. So here the normalization constant a is equal to 1 by root over of minus 3 square is 9 plus 1 square is 10. So this is 1 by root over 10. So this is basically eigenvector for eigenvalue lambda is equal to 3 is 1 by root over 10 minus 3 1 plus 2. So this is your one answer. Okay, and the other answer would be, what is the eigenvector for lambda is equal to minus 1. So this is basically 2 minus 3 minus 1 0. So 2 minus 3 minus 1 0, x1 x2 is equal to minus 1 x1 x2. Okay, so what you get is 2x1 minus 3x2 equal to minus x1, and minus x1 plus 0 is equal to minus x2. So x1 3x1 is equal to 3x2. So from both of these you get x1 equal to x2. That means your eigenvector psi x in this case is x1 x2, which is 1 and 1, and if you normalize it, it will be 1 by root over 1 square plus 1 square, then 1 plus 2, which is 1 by root over 2 1 plus 2. So this is eigenvector for eigenvalue lambda is equal to minus 1. So you have got both of the answers, eigenvalue and eigenvector problem. So the easy part is to convert it into a matrix, so that it is easier to formulate like basic math physics to get the eigenvalue and eigenvector. So these are, so there was another a multiplied, so whatever you got as 3, it will be 3a, and whatever you got as minus 1, it will be minus a. So this is minus a comma 3a, and these are the correct answer. So correct option is D. Now question number 9 is, suppose a particle is in state P is equal to this, where a 1 2 3 are orthonormal basis vectors. For an observable B is equal to a plus b something, the probability of measuring B in such a state is what? So you have a particle in this state where these are the basis vectors, these are orthonormal, that means orthogonal and normalized. The observable is this, then the probability of measuring B in such a state. So first of all, the probability of measuring B in such a state only comes from this B is associated with the state 3, right? Because this observable has A 1 1, so A comes with the state 1, and this projection operator of 3 is coming with the coefficient B. That means only if it operates on a state 3, then only you get this probability of corresponding to B, of measuring B, because then this term will be cancelled out, because if you operate it, take the expectation value with respect to 3, let's say, then obviously 1 and 3, they are orthogonal to each other, so this will be 0 and this will be so B 3 3, so this will be 1, that means this will be actually B. So the probability of getting B out of this observable capital B is that you have to take it on the state 3. or you have to get the probability of the particle to be in the state 3 out of this whole state P. So that is very simple and similar thing you have done earlier, that whenever this total state is in components of states 1, 2 and 3, and you have to get the probability associated with 3 basis state, so then you have to take 3 ket, sorry 3 bra and then P ket, and then whole mod square is the probability of the state of particle being in the basis state 3. Okay, but here you have to ensure that this P state is initially normalized, that means it has the normalization factor included, so that this P and P inner product is 1. So you can cross check that whether this is 1 or not, otherwise you have to add another denominator term which is PP. But here P inner product with P is 1 by root over 20 means 1 by 20, then 3 squared minus 2i into plus 2i is basically minus 4i squared plus root over 7 is 7. That means this is 1 by 20, 9 plus 4 plus 7, which is 20 by 20, which is 1. So it is already normalized. That means this term, even if it is there, it is 1. So only have to get what is 3p inner product whole mod square. So that is basically 3 has this coefficient root over 7 by root over 20, which is root over 7 by root over 20 whole square, which is 7 by 20. So your answer of this will be 7 by 20. Okay, so this is your question number 9. Before that, up to that was question number 8. So let us draw a boundary. Okay. Now question number 10 is, in a system described by 3 orthonormal bases 1, 2 and 3, the operator form an observable A is given as this. Then the possible measurable values of the observable A will be what? So basically 1, 2 and 3 are again orthonormal basis vectors, and the observable is A given in terms of 1, 2 and 3 projection operators. Now possible measurable values of the observable A will be, so to get that possible measurable values mean you have to take the expectation values of the you have to take the expectation values, not expectation values, so the possible measurable values of the observable A. So that will be basically very simple answer is that, because you can see that there are observable has 3 parts. One is in terms of projection operator 1, then 2 and then 3. So the system can be either in the state 1 and then you get the coefficient with 1, that is 7, then if state 2 then you get 9, and if state 3 you get 5. So the values you will get from here, from the observable, if the state is either 1, 2 or 3, will be corresponding coefficient values, which are basically 7, 9 and minus 5. So the answer will be 7, 9 and minus 5, because these are the corresponding coefficients of it. So if the state is probable of being at 1, so you will get the observable measured as 7. If it is at 2, then you will get the observable measured as 9, and if it is at 3, then your observable value will be measured as minus 5. So that is the correct answer that you have to give. So it is nothing but based on the expectation value of taking the observable, because that gives you the physically measurable quantity. So the expectation value depends at what state you are actually taking the expectation value on. So here, because any particular state is not given, so the state you will be taking will either be an individual basis state like 1, 2 or 3, and then based on which basis state you are at, so the measured value will be different, and out of these 3, 7, 9 and minus 5. So this is your correct answer, option number D. So we have finished these 10 questions for this class. We'll solve in the next class again.